First of all, welcome. Good morning. Welcome to the talk. I'm truly happy to see so many of you willingly come to hear me speak. It's not every day that I get to see so many of you. My name is Robert. As Martin said, I'm one of those software engineer people. I work for this company called River Digital. We do e-commerce at a fairly large scale, and we do some of it in Clojure, which makes me particularly happy. But the reason I'm here today is because I'd like to talk to you about machine learning a bit. Now, to be perfectly frank, I'm not here to lie to you. I'm not here to tell you that it's sort of the future, that it's going to cure all sadness in the world and deter the apocalypse, what have you. What I'm here to tell you is that you need not know too much about machine learning to actually do something fun and practical with it. And the reason I think this is because I believe functional programming would or can simplify the way we encode machine learning algorithms, and Clojure, being the beautiful language that it is, can simplify it even more. Now, I'd like to show you exactly what I mean. So for this little talk, I've picked one specific domain of machine learning that I like, called reinforcement learning. And I'd like to show you exactly how you can sort of understand it and implement something with it. Now, just as a show of hands, how many of you have heard of reinforcement learning before? Oh, okay, that's a lot of people. Okay, for those of you who don't know it, how many of you own some kind of pet or a child or children? Okay. Some of you, right. Own is the key word there. Right, so how many of you have tried teaching your pet or your child to do some specific behavior by letting it do whatever it wanted, but every time it did the things that you wanted, you gave it a reward, and every time it did something else, you gave it sort of like a punishment or like a scolding, indicating that it did something wrong? Well, at least how many of you have heard of this method of teaching? Okay, a lot of you. So, in the end, what did your subject, so to speak, learn? What did it realize? Well, it realized that in certain situations, if it were to pick some actions, it would get a reward for them. If it were to pick others, it would get a punishment. So naturally, it liked rewards, so it always started to pick those actions that always led to a reward. Now, what this meant for you, basically, was that your subject started to behave exactly the way you wanted. It started to behave optimally with respect to what definition of optimality you've defined, because it's that you were the ones that defined the system. Now, reinforcement learning is the branch of machine learning that uses this type of learning in order to solve problems of optimality. And so practical applications of this are, for example, you want to teach a bot or an agent, as they're called in machine learning, how to win at games or how to play games very well, like chess or Go or StarCraft. Or you can go one step further and say, I want to teach an agent how to control factory machines in such a way that at the end of the month, the output of the factory gets maximized, but the power usage is kept at a minimum. So problems where I need some sort of optimal control in order to do very well. Now, if you ever have one such problem, you could try solving it with reinforcement learning. And the way you do this is by defining your problem as a reinforcement learning problem, which basically just means that you have to physically define this environment where a thing can roam about, try to solve your problem, and for every trial that it does, it gets rewarded or punished respectively. Now, this thing in time is going to realize which things led it to a reward and which things did not, and will converge to sort of the behavior that will always lead to a reward, thus basically meaning that it will behave optimally. Now, if you ever want to do this, you have to define this environment in terms of 5 quantities. And to make it a bit more simple, I'm going to try to define this based on an example. I'm going to take an example and define these 5 quantities forward just to give an idea of how it works. And let's assume that we want to create a bot that learns to play chess very well, right? So how would I define this environment for chess? The first quantity that I need to define for this thing is the state space. Now, the state space is basically sort of all the individual unique situations that may occur whilst my agent is trying to solve my problem. Now, in chess, my agent is going to try to learn by playing chess. And every time he plays, he may very well encounter different positions of pieces on the board. So he may encounter this one, or this one, or this one, or any other of the 10 to the 47 different positions that exist in chess. It's quite a lot. But that's basically what I mean with each individual situation. There's a small problem that he has to solve in order to get to the next one until he solves the game. Now, the next quantity is the so-called action space. These are basically the things that the agent is allowed to do in each individual situation. And these are unique to each individual situation. So, for example, in chess, if I were to be given this board, the rules of chess tell me that there are only a certain amount of pieces I'm allowed to move in this position. I can either move pawns, or I can either move knights, but I can't move bishops or queens or rooks or any other piece. But in other positions, I may very well be. So you can think about this action space as sort of like a function. If you give me a state, I can tell you what actions you can do in that state. The next quantity is the reward space, and this is fairly straightforward. These are basically the reinforcements that I give to my agent every time he makes a choice. Now, the question is, what is a choice? And a choice is basically this idea that when he's presented with a state, he picks an action. By picking an action, he makes a choice, and you give him a reward for that choice made. And this basically tells him how good it was to do that particular thing in that particular state. And you can think about this as a function. For every state and action, there is an associated reward with it, which can either be a value, or can either be cookies, or can either be chocolate, or whatever you want. Now, the next quantity is called the so-called transitions. I'm going to be done with these in a second. So the transitions, or the transition space, is basically what happens after I make a choice. Every time I visit a state and I pick an action, I automatically transition, or the agent automatically transitions into a new state, where he has to repeat the process. Now, if you think about it in chess, if I'm given a position of pieces, and I choose to move a piece, once I've moved the piece, I get a new unique position, which means a new state, where I have to reassess my state, so to speak, and do the same, pick another action. Now, you can think about this quantity, again, as a function. If you give me a state and an action, I'll tell you where you're going to be going, what's the next state that follows. And the last quantity are the so-called terminal states. Now, this is a subset of the whole state space, and these are the states where the agent basically has nothing left to do. There are no actions to pick from, and you can think about it as being the end of the game. In chess, these are the positions where I've either been checkmated, or I checkmated, or there's some sort of draw. So from that point onwards, I can't do anything anymore to sort of try to win the game. Now, you can think about this again as a function. Very functional, isn't it? And you can think about it in terms of a predicate. If you give me a state, I can tell you if it's a terminal state or if it's not a terminal state. Now, if you ever have a reinforcement learning problem, or an optimality problem, and you want to solve it with reinforcement learning, just define these 5 quantities, and you can start throwing reinforcement learning algorithms at it. Now, the question is, how does the agent actually learn based on these things? So the agent himself doesn't actually have any idea about the problem he's trying to solve. He only knows how to accumulate experience and how to use it for his own good. But he has no idea what he actually is doing. He can be playing games, he can be, I don't know, eating chocolate, whatever you want. So what you basically do is you give this agent sort of like a starting state, like a starting situation to look at. He looks at the state, and then he gets the actions of this state. Now, the agent's responsibility is to pick one of these actions, and he does this with something called a policy. Now, this policy is sort of like a strategy with which he picks actions. It could either be a random policy, it could be a function that just picks random actions, or it could be a policy that uses his prior experience to make more informed decisions, like, has he been in this position before? Has he chosen something before that gave him a better reward, and so on and so forth. But for the sake of argument, let's just say that it's just random. So the agent picks one of these actions. He gets a reward for the choice that he's made. He's quite happy. And this reward is going to be some kind of numeric value. Now, the agent is going to commit this action and transition to the next state. And upon transitioning, he's going to keep track of the choice that he's made. And the way this works is that he's going to store the choice that he made in something called his Q values. Now, these are the agent's experience, so to speak. And you can think about them as being sort of like a hash map. In his hash map, at that state, he picked that action, and he got some reward of +1 for it, German. Now, he's not going to store the reward explicitly, but he's going to basically use it to compute sort of like the goodness of that state in action for what experience he had before. Now, the formulas he uses are basically indigenous to the algorithms that you use, so I'm not going to go into detail in them. But it computes basically sort of like a double value, and the tendency in reinforcement learning is that the higher the value, the better it is to pick that action in that state, or the higher the probability that the agent will get to a reward in the end. Now, with this newly found experience, the agent is going to take it and repeat the process in this new state. It's going to get the actions of the state, pick an action, get a reward, transition, and then store his new experience. And he's going to do this over and over and over again until he gets to one of the end states where he basically stops. He has nothing left to do, basically completing an iteration of the game. Now, upon completion, he's going to take his experience with him. He's going to be quite happy. But you're then going to force him at the beginning again. You're going to put him and force him to do another iteration. But this time, he gets to keep the experience that he's gathered, and he gets to use it in this new iteration. And you repeat this process over and over and over again for as many iterations as you want. And with each new iteration, he gets more experience. He refines his existing one, and he learns more and more about your problem. In this case, it would be chess. Now, the last question is, how does the agent actually derive an optimal solution from all the things that he's done? Now, I've told you that the tendency is that the higher the values in the Q values that he has, the better it is to pick those actions. So what he basically does is, with the experience that he has, is he's always going to pick greedily with respect of the action that he has. So in this case, in this state, the action with the highest value is A3, so he's going to always pick A3, and he's going to the next state, pick again the highest value, pick again the highest value, which this basically translates into is, in chess, for example, he's always going to play the strongest moves that he knows so far. And that's how you define, or that's how you derive optimality. But this is basically dependent on how much he's learned. Now, that's basically it. That's reinforcement learning. You need not know more about it. It's fairly abstract, and it's fairly simple to understand. And I'd like to show you that you actually need not know more in order to do something with it. So I would like to implement with you together an algorithm of this domain. And the algorithm that I've chosen is Q-learning. Has anybody of you heard of Q-learning before? OK, some of you. Brilliant. So Q-learning looks like this. You'll find various definitions of the algorithm in various books slightly altered. This is the one that I chose. And what I'd like to show you is that it's fairly easy to take this abstract definition and translate it into code almost as it is. Now, I have a question. How much time do I still have? 20 minutes. OK, that's more than enough. So let's get started. So let me just zoom in. Can you see this? Is it visible at all? Brilliant. OK, let's make it a bit bigger. Right, and I have IntelliJ here at my side. Can you see my code at all? How about now? OK. Right, so let's look at the algorithm. Now, this is basically going to be a function of some kind, right? So let's define a function called Q-learning. And for the sake of argument, I'm going to name the parameters of this function just to make it a bit more clear what data is going to receive. So what does my algorithm say? Well, the first 3 lines are sort of requirements. I require this, I require that, I require this. These are inputs to my function. I need these things in order to run my algorithm. So the first thing that I need is a number of episodes. These episodes are another name for the iterations that I'm going to run my algorithm for. So I'll just define them as an argument. Now, the next one is something called a discount factor gamma and a learning rate alpha. Now, these 2 things I'm not interested at all because these are details of the algorithm. They're parameters that I get. They're values between 0 and 1. I don't really care. So I'll just say I'll get them as a parameter, so a gamma and alpha. And then it says I require starting state S0. Well, why not get that as well? Now, the next line basically says, ensure that you initialize all the states and actions in your Q values. This Q thing there is the Q values, this hash map of the agent. Now, in Clojure, I don't need to initialize a hash map with default values. I can just define an empty one and then work with it as I go along. So that's basically it. And then the algorithm starts and says, well, for 0 to n, do. Now, I can range over all the episodes. And with each iteration, if you remember, I'm going to update my Q values. So a sane way of doing this is reducing over this whole thing with my Q values. And with each iteration that happens, I can then apply the algorithm. So on the left side, I'll have my new Q values. On the right side, I'll have my episode. Just for the sake of argument, just print line the episode. And let's see what the algorithm says to do. It says, initialize some state S with my initial state, and while S is not terminal, do something. Now, this seems oddly like a loop. So let's define a loop called S with my S0, and then while S is not terminal, do. Now, this terminal thing seems like one of the quantities that I've defined before. And I've told you you can think about it as being a predicate. So why not model it as a predicate? And why not say that I'm going to receive it as a parameter to my function? And then I can implement this. I can say, if not terminal my state, then do something. The next two lines are a bit more tricky. The next two lines are basically this learning step that the agent does. It basically says, pick an action A with this pi thing. This pi is basically a name for the policy. Pick an action A, take that action, look at the state that you're going to go into, and look at the reward that you receive. Now, these are all things that come from my quantities of the world, from my action space, from my transition space, from my reward space, and so on and so forth. And I've told you you can think about them again as being like functions. So why not model them as functions? Because we're functional programmers. So I have an actions function, I have a transition function, I have a reward function, and I most probably also have a policy with which I can pick actions with. So I can implement this thing. I can pick an action with my policy. Now, my policy generally receives the state that I'm in, the actions of that state, and the agent's experience. If it needs to do some sort of informed decisions, it needs all of these things. Now, I look at the reward that I receive with my reward function that takes an action, it takes the state and the action. Then I transition to my new state, S prime, with my transition function. And that's basically the first 3 lines of the algorithm, or 2 lines. Now, the next line is a bit more tricky. It says, pick an action A prime with this argmax thing. So how many of you have heard of argmax before? Okay, so argmax is basically like a max by function. Give me the largest argument where the value of that argument is largest. And you can implement it in Clojure fairly simply. So let's say A prime, in my Q values, look at the actions that I have for that state. Or if I could only type. Then max by their values. Then I'm going to get the entry of them at that point, then get the key, basically being the action, and then get the first value. And that's basically the greediest action that the agent knows of at that point in time. Now, it could very well be that my agent has no prior experience for this state. It could very well be that he hasn't explored this state before. So in that case, I can do the following. I can say, instead, so if you don't have any prior experience, just pick a random value from the actions of that state. If I don't know anything about, just pick a random value just to be able to continue with the algorithm. And now comes the last line. Now comes the point where you have to update your experience. And this line basically states, it says, in your Q values, at that state and at that action, just replace that value with whatever this is going to return. Now, I don't need to understand what this does because I have all the data that I need, so I can just write it down. So let's get in my Q values the value at that state and action. If I don't know anything about it, I'm going to return 0. Then get S prime, A prime, get in my Q values. And then I can compute my new value. So I can let me just write it down. So QSA plus gamma, alpha, it was, times R plus gamma times Q S prime A prime, and you subtract from this thing QSA. And that's basically it. You just write the equation down, you get a value. What this value is, you don't care. So now, what my algorithm says is recur with this new state S prime. Now, in this, when I'm going to recur, I'm going to go to the new state and repeat this whole process. But right now, I don't keep track of my Q values as I go along. So being a loop, I have to basically take them with me. So let me put my Q values in here, and then recur, and then say a sock in my Q values at that state, at that action, this new number that I get. Now, I'll do this until I get to my end state. And once I get to my end state, I've completed one iteration, and then I'm going to return my Q values, and then do another iteration, and another, and another, and another, and another. And for all intents and purposes, this is basically the implementation of this in Clojure, which is quite simple. It's almost one-to-one the same thing. Now, there's one last thing that I need, namely a way to derive the most optimal path based on the experience that the agent has accumulated. And I've told you to derive the optimal path, you just start at the state and always pick the greediest actions. Now, I'm not going to implement this directly for you. I have it somewhere here, because it's quite simple to implement. I'm just going to copy it and paste it. But the idea is simple. You start a loop with the starting state, then you accumulate the optimum, and while it's not terminal, you pick the greediest action, you transition to that state, and you just accumulate all of these things. And that's basically it. Now, I'd like to actually use this thing on a problem and show you that it hopefully works. Hopefully. So, let me start my REPL. Right. If it would only start. So about 2 years ago, black and white, yeah. Look and feel IntelliJ. It's better? Yeah, brilliant. Okay. So about 2 years ago, I've created sort of like a little sandbox where you can test reinforcement learning algorithms. And in this sandbox, you had this little game where you had to teach this agent here how to safely get from this point to this point. Now, for this world, I've defined all the quantities necessary. I've defined actions, transitions, whatever you want. So I can just use my algorithm on this little game and see if it works or not. Hopefully it does. Oh, I messed it up. Of course I did. Okay, better. Right. So let's define sort of like the configuration of my algorithm. The first thing that I wanted was a number of episodes. So let's just say that I want to run this for about 300 iterations. The next one was the sort of the whole quantity. So the transition, I have a transition function. The reward, I have the reward function. The actions, I have the actions function. I have a starting state. Gamma is one of these parameters from 0 to 1. I'm going to pick it to be 1. And alpha is the other parameters. I'm going to pick it to be 0.3. Now, these have a meaning, but for now, let's leave them at that. The next thing that I need to define is a policy. Now, I told you can define a policy that is arbitrary. You can pick arbitrary actions, but that doesn't really make sense. So let's pick another. We'll pick one that's called epsilon greedy, which just basically is a fancy name for a policy that you pick a probability, and with that probability, the agent is going to pick a random action. When with one minus that probability, you're going to pick the greediest action that he knows of. So I'll pick a 70% probability. 70% he's going to explore. 30% he's going to do whatever he's done before. And then the last thing that I need is a terminal function, and that's basically it. Now, let's run the algorithm and see if it fails or not. And as you can see, it learns for about 300 episodes. We're not going to see it in the render itself because you won't understand anything. But if I look at the Q values, you'll basically see that it's a big hash map with a lot of values inside of it. Now, I can use the solution function to derive an optimal solution for this. And let's see if it can. Let's take the Q values, let's take the data. And it did derive an optimal solution. So what I would like now is to render this solution and show you what path the agent learned. So right now, I would like you to not look at the code that I'm writing, but at the little game there. Result channel. And let's see what it found out. Magic. Yes! Right, let's look at it again. Right, brilliant. So that's all that you needed to do in order to just implement an algorithm and use it on something fun and practical. And that's what I said. You don't need to understand much of it. If you want to go into the nitty-gritty and understand what these alphas and gammas do, of course, you can start reading a lot of literature. But just the beauty of Clojure is that you can almost one-to-one translate these things without any problem, just with a bit of different thinking that functional programming generally gives you. Now, that's the end of my talk. I do thank you for your patience. I hope this was interesting. And if you have any questions, I'm glad to answer them. Thank you.
Thank you very much, Robert. That was excellent, I thought.
Thank you.
I think we do have time for a few questions, if there are any questions. Are there questions? I guess I should be asking. Oh. Okay. I have one. Oh, okay.
Yeah.
Hi.
Hi.
My question is about the chess example.
Yeah.
So it will not kind of think ahead in this simple setup, right?
No.
So it will only ever think in this situation, this move was the best, but it cannot change that a few moves back to realize, oh,
well, the
put
algorithm.
my bishop there a few moves back was bad. You would need an LSTM for that or something.
No, so the algorithms themselves will, just by means of playing, correct these errors if he were to ever visit the positions that he did before. So if in the past he's made some error, he's most probably, by playing, going to come to that situation again. He's going to most probably play something else and realize that he might choose something else to get to a better outcome. But the algorithms themselves, sort of some of them at least, guarantee that this convergence, that he's going to find the best moves just by playing. So if you give him enough time, at some point in time, he's going to find out that there has been a better move back about 3 moves ago. Yes?
Just another question about the chess example.
Yeah.
The space of state.
Yeah.
And also the number of possible actions is
Yeah.
quite large.
Yeah.
About 10 to the power of 120 possible games in chess.
Yeah.
And how's the algorithm drilling down the solution space? Because no computer can
It's not.
save all the
Yeah. So,
all the rewards for the positions.
so this is a combination of both the policy that you're using. So the policy basically decides how he's going to pick actions, and it can either make informed decisions like, he's seen this before, he's tried this move before, he got sort of like a good result out of it, he's going to try it again. Otherwise, he can explore. But the problem in chess is that the state space is extremely big. So you can't just store it in a hash table. So what you do then in these situations, you use a function approximator to approximate this Q-value thing, and that could be sort of like a neural network of some kind.
Is this comparable to what Google did with AlphaZero?
AlphaZero is an interesting case because, yes, on the one hand it is because they thought it with reinforcement learning means. So they basically defined this environment where the agent played against himself, and he got rewards for the games he played. But the way it learned, so the Q values, how they were represented, and the way he picked actions, the policy itself, they were different and they were a bit more complex. But from a problem standpoint, how they solved it, yes, this is the way that they went forward.
More questions? Okay, there we have one more. I hope I get to ask my question too.
Yes.
Thank you for the talk. I actually tried reinforcement learning last year. There was this competition called General Game AI competition.
Yeah.
And in here, you are supposed to like summon your agent and get scored by some unknown games in the. I failed. Because
we all do.
I tried with some toy examples like keep your stick and not fall down and stuff, but the minimum example game they gave was kind of space invader kind of game, like the aliens and you shoot with your airplane and stuff. My problem was, I think it was about efficiency. So when you are saving Q state, I was letting my agent learn about this game, and then it because you have to save the Q state and like try it out in the later. It just filled up my laptop storage completely, like like gigabytes and gigabytes. Were used like in matters of minutes. So do you think I wrote some terribly inefficient algorithm, or is it general problem expected in reinforcement learning, or like what do you do with the resources?
I think it's not a problem. It's you've went the right way. The thing is, the problem that you were trying to solve was a bit too big, like chess. You had too many states. It was probably sort of like a discrete problem. It was this thing where you had a pole and you had to keep it straight, wasn't it? That's the standard example. That's a very discrete problem. Now, you can't solve all problems with just a hash map and storing it, because the states get too big. So in that case, you have to start thinking a bit more clever. You have to start defining sort of like things that can approximate this Q table in some way or form. And if you use, for example, function approximator, we use like a feature vector to describe your world. And instead of storing values in the Q values, you use the reward to tweak your feature vectors. You can more or less approximate the same things that you would otherwise have with the proper hash map. So if your problem gets too big, the storing of states and actions in a table is not viable for you. So you have to go into other means or other realms. These are described in all the reinforcement learning books, and they're called function approximation methods, basically. Yes. No problem.
That was a very good answer. Okay, I think we might have time for one more question if someone's particularly excited. Otherwise, I'm going to ask the last question. Okay. No, it's all right.
May I?
Yeah.
Thank you. You showed us a very beautiful implementation of this stuff that usually, well, not usually, but this stuff often gets done in Python.
Yeah.
And it is very, there's a lot of frameworks and there's a lot of also hardware support because it usually gets done on the GPU.
Yeah.
And what would you say is there a performance difference in doing this in Clojure instead of in Python, or could you tell us anything about the performance?
So I could tell you that Python has better support for reinforcement learning simply because the whole machine learning sort of community veered towards that area. I don't know why, because I believe Python as a language is quite slow. But Clojure in itself for numeric computation is also quite slow. But I do believe that Clojure could be a bit faster, and I think Clojure in general allows you to better translate these algorithms into something, like you've seen, more beautiful. Now, I can't tell you anything about performance impacts because both languages will not perform as well as if you were to write them in C and then throw them on your GPU. But my biased opinion is use Clojure instead of Python.
Okay. I think with that, we're going to close it. Please give another round of applause for Robert and his great talk. Kevin.
You set us up with your question.
Oh, you're now all curious what my question is. Should I ask my question? Okay. Thank you, Kevin. Thank you so much. No, I was just wondering in like the chess example, it's sometimes a little hard to see what the reward is. Like if you move the knight in the first round, there's no consequence, right? That where you can see what the reward for that is. How do you deal with that kind of situation?
So the reward space is one of the most complicated things to define in reinforcement learning because how you define rewards is going to define how well your agent is going to learn. Now, in chess, the standard example is just to reward him if he's won the game, not immediately. So you let him just play about, and when he gets to the end, if he's won, he gets +1. If he's lost, he gets -1. If he's drawn, he gets a 0. But because you don't have any immediate sort of rewards. But in other problems, you may very well have them.
Yeah, okay. So in some situations, there just is no reward, and you sort of skip over that until you have some insight about that was good or bad.
Yeah.
Okay, thank you very much. Now you have to clap again.